So, good morning. In the last lecture, which is already a week ago, we discussed about higher order functions, how to use higher order functions in programming. And in particular, we identified certain specific higher order functions which implement certain forms of recursion structures. So we had some functions like map or fold. So we had higher order functions. And we had functions like map or filter or fold and so on. And they can be used to implement certain recursion structures that are often used. And by using these higher order functions in your implementations, well, you can reuse these recursive structures again and again. And the effect is that the resulting algorithms are very short, very readable, and very easy to reuse. And of course, you can also implement such higher order functions yourself. For example, if you introduce new data types, which are not predefined, then you have to program something like this yourself. And moreover, there can be recursion structures that are not predefined, but that you might want to use in many, many functions, and then it's a good idea to implement something like this yourself. Now, before we end this chapter on higher order functions, I want to show you another use of higher order functions. Namely, higher order functions can also be used in order to realize a certain form of notation that is very convenient. So this is something which is very nice to write, very nice to read, and you can only realize it because you have higher order functions. And that is the concept of list comprehensions. So apart from this, you can also use higher order functions to build so-called list comprehensions. And these are basically just this is just a nice syntactic notation which is easy to read and which makes it possible to formulate very short and concise programs. So short notation for certain forms of lists. So we spoke about these recursion structures by higher order functions, but list comprehensions we did not yet discuss, so that's what I want to do now. Okay, so the idea of list comprehensions is very simple at first sight. In mathematics, you would often write something like this. In mathematics, you are used to writing sets in the following form. You would, for example, say, I want to regard the set of all values of the forms x times x, so all squares, where, and now you make this vertical bar, where x is a member of the element 1 to 5, and moreover, x is an odd number. Now this notation hopefully looks very familiar to you. You're used to this from mathematics. And, well, what is this set? This set, to compute this set, you take all x's from this set, 1 to 5. But then you don't take all of them, only those which are odd. So only 1, 3, and 5. And you compute their squares. So 1 square, 3 square, 5 square, which is 1, 9, and 25. Now, this hopefully looks very familiar to you. And in Haskell, you can write almost the same. So in Haskell, you can write something like this. You can say, I want to look at the list of all expressions of the forms x times x, where x is an element of the following list, and you write this by this arrow to the left. So x is an element of the list 1 to 5, and x is odd. Now, you will agree that this looks very similar to this. And if you write this expression in Haskell, it will evaluate to the following thing. For x, so the idea is the following. you produce the list of all these expressions, but the value of this variable runs over all elements that are from the list that is generated here. So x takes on all values from 1 to 5, but then you restrict it again by just looking at those x's which are odd, so 1, 3, and 5, and you square them. So you get the list 1, 9, 25. So this nice notation that you know from mathematics, you also have in Haskell. Now, let's analyze this in a bit more detail. This here is just a short notation that is present in Haskell. So this is a short notation in Haskell. So you can, if a and b's are integers, you can write square bracket a and then 2 dots b. And this gives you the list a plus 1, dot, 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 until b. And so how are these list comprehensions built in general? So in general, this thing is called a list comprehension. The general form of a list comprehension is as follows. A list comprehension computes a list, and the list is a list of values which are given by this expression. So here the expression was x times x. So the list contains all of these expressions where the values in this expression take on several. The variables take on several values, and which values they take on is given by the part after the vertical bar. And these expressions which say which values these variables take on are called qualifiers. So here you may have many qualifiers, qualifier 1 until qualifier n. Something like this is called a qualifier. And there are two forms of qualifiers which you can both see in this example. So we have two forms of qualifiers. So-called generators and so-called guards. Now, what is a generator? A generator is a qualifier which generates values. So something like this expression, x, and then an arrow to the left, and then the list 1 to 5 is a generator, because this generates the values 1, 2, 3, 4, 5 for x. So this means let x take on the value 1, and then take on value 2, and then take on value 3, and so on. So this is called a generator, and the general form of this looks like this. Let this variable take on all values from this list. So this expression describes a list, and the meaning is the variable should take all values in the list x. And a guard restricts the values. So a guard is something like odd x. So the guard says, well, up to now, x would take on all values 1, 2, 3, 4, 5. But now we don't want all of these values, but only those values which satisfy this Boolean expression. So a guard is a Boolean expression, and it restricts the values that can be used, because it says, well, if this guard is not satisfied, then don't use this value. So a guard is something like it's a Boolean expression, and it restricts the values of these variables. So an example for this is odd x, and here for the generators an example is x should take on all values from the list 1 until 5. Now this looks rather intuitive, but to define this formally, one indeed needs higher order functions. So at the moment you probably don't see what this has to do with higher order functions. Now this notation is really just syntactic sugar. This is just an abbreviation. You can define what this means by the use of other functions, in particular by the use of higher order functions, and the main higher order function you need here is map. So the formal definition is as follows. The formal definition is as follows, and it shows that list comprehensions are really just abbreviations for normal common expressions which use the higher order function map. Which use the higher order function map. And, well, what is the actual definition? Now the definition is as this. If you have, formal definition has two parts, depending on whether the first qualifier is a generator or a guard. If it's a generator, then it looks like this. So the first qualifier would be a generator, which looks like this. And then we have Q, and this should simply be a list of qualifiers. So this means we have a list comprehension where the first qualifier is a generator, and then there may be many additional qualifiers. This is a list of qualifiers. So this is the first case, and the other case is when the first qualifier is a guard and not a generator. And now, the meaning of this is as follows. I will first write it down, and then I will try to explain what it means. So this is a shorthand abbreviation for a complicated-looking expression using map. And the expression looks like this. I will explain it to you in a moment. Concat is predefined, and what concat does is it takes a list of lists and unites all the lists in there. So concat, if you give it a list of, let's say, x1, x2, and then the list x3, and then the list x4, x5, then the outcome will be the list x1 until x5. So this is what concat does. We defined concat in the last lecture ourselves, but in reality this is predefined. It takes a list of lists and simply gives you back the list which contains all the elements. Okay, so this is concat of the following thing. It concatenates, so now we need a list of lists. And the list of lists is this one. So what we do is we take this expression and we apply a certain function f on all the elements of this expression. This expression prime is a list. The meaning is the variable should take on all the values in this list. So we want this variable to take on all the values in this list, and then the result should be this expression. This expression, but the variable first takes on element 1 in this list, then element 2, and so on. This is realized by this map expression because this f is defined as follows. F of this variable that is bound by the qualifier is expression under the rest of qualifiers. So the meaning is as follows. Let's look at what this might mean. And I will try to illustrate this on the slide. So this is what we had before. These are list comprehensions, and this is the definition that I just wrote on the board. Now, what does this really mean? Now, as I said, in such a list comprehension, if you write a qualifier, this expression prime is a list. So this expression prime is a list. This is a list. For example, something like a list of elements A1 ... AN. Okay, so what is the meaning of this? Well, let's just execute this definition and see what happens. So if we execute this definition, we would get this. So by this definition, this is the list that we get by uniting all these lists in there. And in these lists, what we do is we take this list from the qualifier and we apply the function f to each element of the list. So what we get is this. So map does the following thing. If we apply map applies f to each element of these lists. So the outcome of this would be the list consisting of f of A1, f of A2, f of AN. I mean, so if expression prime is this list, then map f, this list means apply f to each element. Apply f to element A1, f to element A2, f to element AN. So you would get this. And now concat, these are all lists. This is a list, this is a list. And concat simply takes a list of lists and unites them all, concatenates them all. So this is the meaning of this. Take the first element, the first list, and then append it to the next list, and then append it to the last list. Now, so this is what the outcome. What will happen is that this function f will be applied to all the elements in this expression prime list. And now, what does this mean? F of A1. F of A1 means we take the remaining list comprehension where we drop this first qualifier. So we take this expression, but in this expression, the variable is now instantiated by A1, because we apply f to A1. If we apply f to A1, you will get this result, but everywhere where the variable is, you now have A1. So it would be just this. So f of A1, let's look how f is defined. It's this thing over here. It's the remaining expression under the remaining qualifiers without the qualifier that we just, without the first qualifier. But if we instantiate this variable by A1, then the variable has to be replaced by A1, and this x is nonsense. So this x should be this variable that we just replace here. So here we should have the variable that we just replaced is now replaced by A1, and here the variable is now replaced by AN. So if we want to execute this in our example, what we would get is this. So I have to continue this definition because I still need the case with the guards. But maybe I first illustrate this in the example. So maybe it's a good idea to leave some space after this definition because it's not yet finished. So if we look at the example that we had, if we take x times x, where x comes from the list 1 to 5, and x is odd, then by this definition, this is nothing but concat of map f and then the list 1 to 5, where f of x is x times x, but now we drop this first qualifier. So this means this is the list of all square numbers provided, so of all expressions of the form x square where x is odd. So 1 square, 3 square, 5 square, 7 square, 9 square. It's an infinite list. And, no, sorry, it's not an infinite list. If you give f an element, you get back a one-element list containing, so f of 1 is the list containing 1 square. F of 2 is the list which is empty, because f of 2 would contain 2 square, provided that 2 would be odd, but 2 is not odd. So f of 3 would be the list containing 9. F of 4 would be empty. F of 5 would be the list just containing 25, and so on. Okay, and concat. Now if we look at this expression, this means build the list where you have f of 1, f of 2, f of 3, f of 4, f of 5. So it's this list, f of 1, f of 2, until f of 5. And here we get the same thing. And concat means unite all these lists. So take the list f1 and then append it with f2 and then append it with f3 until f5, and this is still the same. Okay, so if we now execute this like this, we would get x times x, if odd x, but x is replaced by 1 here, by 2 here, by 3 here, and so on. So here we would have 1 times 1 if 1 is odd. This is appended to 2 times 2 if 2 is odd, and so on. And this is appended to 5 times 5 if 5 is odd. So this is simply executing this definition. Okay, now to finish this example, we would have to know how to deal with list comprehensions where the first qualifier is a guard and not a generator. And therefore, to finish this example, we have to finish the definition. So let me do this. What is the definition of such a list comprehension? If the first qualifier is such a Boolean expression, and then there may be many other qualifiers. So this is a Boolean expression. Now, what happens here, this is a Boolean expression. So what happens is that one simply tests whether the expression is true or false. If it's true, then it plays no role. Then you just can remove it, and the result will be the same as if you had no expression. If it's false, then the result is the empty list. So this is an abbreviation for if this expression is true, then you can drop it. So then it's the same as this. And if it's not true, then the result is the empty list. And then finally, if you have no qualifier left, so if Q is empty, then XQ should be the same as just the list exp. So in this way, you can now transform all list comprehensions recursively by taking away one qualifier after another into a big expression without list comprehensions. And this indicates that list comprehensions are really just a shorthand to make things more readable. Now, let's finish our example. So in our example, this means this here is a shorthand for the following expression. It stands for if the guard is true, then the result is the list comprehension without this generator, so it's just 1 times 1, and else it's the empty list. Okay, 1 is odd, so here we get 1 times 1. Now odd 2 is not true, so here we get the empty list. Odd 3 is true, so here we get 3 times 3. Odd 4 is not true, so we get the empty list. And odd 5 is true, so we get 5 times 5. Okay, and if we now finish this, we indeed get the list that we expected, 1, 9, 25. So this is what list comprehensions really mean. And so if you ask yourself, what is the semantics of these list comprehensions? How are they actually evaluated? Then look at the definition. So this is what happens internally. So if you write a list comprehension like this, Haskell will translate them according to this definition, and it will simply evaluate these expressions with concat and map. The list comprehensions are just a more readable way of denoting it. And to see how to use list comprehensions and what they really mean, I mean, you have the formal definition now, but we can look at some more examples to get a feeling for how they work and what they are good for. Okay, so some more examples. Now, as you can see from this definition, the order of the qualifiers plays a role, because you first take care of the first qualifier, then you look at the next qualifier, and so on. So simply exchanging the order of the qualifiers will also modify the result. And to see this, let's look at this. So here we generate the list of all pairs A and B, where A comes from the list 1, 2, 3, and B comes from the list 1, 2. Now, we can think about what this is compared to the list that we get when we exchange these two qualifiers. So we could also first write B comes from the list 1, 2, and A comes from the list 1 until 3. So what do you think is the first list? Now, intuitively, somehow it's clear. The lists, both lists should contain all pairs A and B, where A is between 1 and 3 and B is between 1 and 2. The question is, in which order? I mean, in lists, the order plays a role. These are not sets, these are lists. So, what is the order? Now, it's rather obvious how the first element looks like. The first element must be 1, 1. Now, the big question is, how does the second element look like? Is it 1, 2, or is it 2, 1? So, who thinks that this element is 1, 2? Who thinks that this element is 2, 1? Okay, so it's like in a real democracy, the majority has won. So, indeed, the second element is 1, 2. And what is the reason? We first execute this qualifier. So this qualifier says A should be bound to 1. And then with this binding of A to 1, we look at the rest, namely, so what we take is, we take all the A's and B's where A is bound to 1, so here we have 1, and B is bound to something between 1 and 2. And this is appended to the list where we have 2B, and here we have the same. And this is appended to the list where we have 3B, and here we have the same. So according to the definition, this is what happens. We first take care of the first qualifier, and the first qualifier says look at the remaining expression if A is 1, look at the remaining expression if A is 2, and look at the remaining expression if A is 3. And therefore, indeed, this will give us this list. And now, obviously, if we do it the other way around, then we first say, okay, B should be 1, and then we look at the remaining list comprehension, and in the remaining list comprehension, A goes from 1 to 3. So we have 1, 1, 2, 1, 3, 1, and then 1, 2, 2, 2, 3, 2. And now, obviously, these lists contain the same elements, but not in the same order. Now, moreover, you can also have list comprehensions where later qualifiers depend on variables that were introduced by earlier qualifiers. So you can also write something like this. The list of all pairs A's and B's, where A goes from 1 to 4, and B goes from A plus 1 to 4. So you see that this expression, which generates B, depends on A. And A was introduced earlier by this qualifier. So what do you think will be the result? Now, I mean, the first value for A is 1. So we first have to look at the remaining thing if A is 1. Now, the remaining thing is let B range over A plus 1. A is 1, so from 2 to 4. So it's 1, 2, 1, 3, 1, 4. And then we look at all the stuff if A is 2. And now B goes from A plus 1 to 4, so from 3 to 4, so it's 2, 3, 2, 4. And then finally here we have 3, 4, and that's it. Because if A is 4, and B should be from the list from 5 to 4, that's not possible. So these lists only work if this thing is less or equal than, so the left border has to be less or equal than the right border. Moreover, the order in which you have generators and guards can be completely arbitrarily. So you can also write something like this. So again, A should be from 1 to 4, but A should be even. B should be from A plus 1 to 4, but B should be odd. Odd B. Now, what do you think is this list? It does not contain very many elements. Any idea? Mm-hmm. Sorry, 2, 3? 2, 3. Only 2, 3, exactly. This is the only element of this list. So, I mean, in principle you might have all of these elements, but you restrict A to be even and B to be odd, and you can easily see that the only pair where A is even and B is odd is this. Okay, now maybe another example. Now these are maybe uninteresting examples, but you can easily use list comprehensions to define functions in a very, very short and concise way. For example, let us define the function map. Now, this function map that we know, of course you can define it without list comprehensions, but if you define it with list comprehensions, it looks much shorter. So let me show you the original definition of map. This is here. So on this slide you can see the original definition of map. So map takes a function G and applies it to each element of a list. So map of G, and then the empty list is empty, and if G is applied to a list, if you take map and a function G and a list which is not empty, you first apply G to the first element and then you call map recursively. Now, if you don't want to use recursion in your definition, but only list comprehension, you can do this differently. So you can say map G and axis should be the list of what? So you can write this in just one single line using list comprehension. Now, how would you write this? So G, and then? Now, if we write it like this is not a generator. A generator has to look like this. A generator has a variable. A generator contains an arrow to the left, and it says this variable should take all values from this expression x prime. So if we want a generator, then we somehow need such an arrow to the left, and on the left-hand side of this arrow we need a variable, and on the right-hand side we need a list. Right. So this means the following. This is the list of all expressions g of x, where x is an element of xs. Now, if you think of mathematics, this is the list of all g of x, where x is from xs. Now, this should look rather familiar to you, and if you write it in Haskell, this looks almost the same. And maybe another example to convince you how useful this is, let's define quicksort. So quicksort is a well-known algorithm if you don't remember it. Here is an implementation in Java. Now, this is completely unreadable. I mean, this is nicely formatted, and this is the standard implementation of quicksort. And if you spend some time on it, you will understand how it works. Now, I don't expect you to understand how it works from this implementation. The idea is very simple. But if you want to formulate it in an imperative language, then it will look like this. If you formulate it in a functional language, then it will look much shorter, and it will be immediately clear what this function does. So this is a standard example to show the advantages of functional programs. Now, the idea of quicksort is as follows. Quicksort the aim of quicksort is to sort a list. So you give a list to quicksort, and then it should return the sorted list. So how would quicksort look like? Okay, I call it qsort again. What should be the type of qsort? Well, let's make it as general as possible, and then quicksort cannot only sort lists of integers, or lists of characters, or lists of floating point numbers. It can sort the list of anything where you have a greater relation. I mean, that's what we want to do. We want to make sure that an element comes before another element if this first element is smaller than the other element. So quicksort could be defined for all lists of type A, provided that the type A has a greater relation. And now, luckily, there is a type class for this called ort. We had that before. So this type class contains all those types where greater is defined. So if A is a type where greater is defined, then we know what quicksort does. Quicksort takes a list of elements of type A and returns a list of elements of type A. Okay, now it will easily fit on this remaining blackboard, so there's no need to wipe. This would never fit on this blackboard, by the way. And how would quicksort work? Now, the idea of quicksort is as follows. It works recursively. So you want to sort your list, so you take out an element, and then you compute those elements of the list that are smaller than this pivot element and those that are greater than this pivot element, and you call quicksort recursively both on those elements that are smaller and then those that are bigger, and then you put together the result by putting the pivot in the middle, the sorted list that was smaller before the pivot, the sorted list of elements that were bigger behind the pivot. That's the idea. So explaining the idea is not too difficult, and writing it down is also not too difficult. So there are two possibilities. If the list is empty, then there is not much to do, then the outcome is the empty list. If the list is not empty, Okay, so as I said, we take one element out of the list. Let's take this one, the first one. So the idea would be we take out the first element of the list and we put this element in the middle. And then we put something before and we put something behind. And before this element, we should take all those elements that are smaller than x, but sort them. So let L1 be the list of those elements in XS which are smaller than x, and let L2 be those elements in the list XS which are greater than x. And then here we put the sorted list which results from sorting L1, and here we put the list which results from sorting L2. So we call quicksort recursively on L1, and we call quicksort recursively on L2. And now what is L1 and L2? So L1 are those elements of this list that are smaller than x, and L2 are those elements that are greater or greater equal than x. I mean, the list may also contain duplicates, so those that are equal to x we either have to put into L1 or to L2. So how can we make sure that L1 are those elements of x's which are smaller than x? Now, of course, we can formulate this in many different ways, but if we want to make it as short as possible, we use list comprehensions. So how can we use list comprehensions to define that L1 should be those elements of x's which are smaller than x? How would we write that? Now, any idea? So if I say list comprehensions, it should start with an opening square bracket. Mm-hmm. Let's not use A because we had A up here. Let's lose Y. So it's common. So typically, I mean, of course you can use A or B, but to make things more readable, we typically use things like A and B for types and things like X, Y, Z for objects. So it's a good idea to use it like that, then there's less confusion. Because it's not wrong if you do it, but therefore I think Y is more readable. Okay, but now please continue. So Y is an element of x's.
And Y is less than x.
Right. And Y is less than x. Okay, and then L2 looks almost the same. These are those Y's which come from x's. But now Y is greater or equal than x. And that's it. So if you know how quicksort works, if you know the idea of the algorithm, then writing this down is absolutely straightforward. And vice versa, if you don't know the idea of quicksort, then by looking at this algorithm, you immediately understand what quicksort does. And that is not true for this Java program, I would say. So I hope this convinces you both that list comprehensions are a nice idea and that functional programming in general is a nice idea. Okay, so this ends the part about higher order functions. As I said, the goal of this part of the lecture is I want to show you how to use the specific features of functional programming languages for actual programming, how to show how to use special features of functional languages in order to program in a particular elegant or efficient way. And well, one special feature of functional programming language is that they have higher order functions, and I've discussed how to use this feature for programming. And the next feature I want to discuss is how to exploit lazy evaluation for programming. So as you know, Haskell has lazy evaluation, so we do this outermost evaluation in contrast to more or less all imperative languages. And now the question is, how can we benefit from this when we want to write actual programs? So this is the next section. So how do we actually program with lazy evaluation? Now, just to recall the evaluation strategy of Haskell, so evaluation in Haskell, the evaluation strategy was like this. In general, evaluation is leftmost, outermost. So you start to evaluate as far to the outside as possible. And if there are alternatives, which are both as far inside and as far outside, so it's not that one evaluation position is more outside than the other, then you take the leftmost. So in general, we have leftmost, outermost evaluation. Now, an exception to this rule are the predefined arithmetic operators and these comparison operators. So something like plus, minus, times, but also like a greater, smaller, or equal. Now, these things do not work with leftmost, outermost evaluation, but they really evaluate their arguments first, and then they apply the operator. So they work in a so-called strict or eager or innermost evaluation mode, just like in other programming languages as well. Now, of course, you can discuss about whether this is a good idea or not. And, well, it is done like this in Haskell. So this is something one at least has to know. So the predefined arithmetic operators, they don't work with leftmost, outermost evaluation. So something like plus, minus, times, and so on. And also comparison operators. So something like greater or greater equal or smaller. They don't do this. So they instead require that their arguments are first evaluated completely. And we've also seen that, okay, we do leftmost, outermost evaluation, but sometimes in order to find out which defining equation of a function you can apply, you have to evaluate the arguments a little bit. So when you do pattern matching, in order to find out which pattern actually matches, the arguments have to be evaluated sometimes. But then we don't evaluate them completely, but only as much as needed. So for pattern matching, arguments are only evaluated as much as needed. So until we can find out which pattern matches. For pattern matching, arguments are only evaluated as much as needed. So an example to demonstrate this is this. Now let's say we want to define the number infinity. So this would be an integer, and we can define this like this. So infinity equals infinity plus 1. Now obviously if you try to evaluate infinity, then this will not terminate. Because infinity evaluates to infinity plus 1. This evaluates to infinity plus 2, infinity plus 3, plus 4, plus 5, and so on. Nevertheless, we can compute with infinity. For example, we can define multiplication as follows. So let's say multiplication on integers works like this. 0 times something is 0. And if we want to multiply x plus 1 with y, then we get y plus multiplication of x and y. So, I mean, this means you have one more y than if you just multiply x and y. And so what happens if we want to evaluate the multiplication of 0 and infinity? Now, what happens if we evaluate this in Haskell? This is 0 because we do outermost evaluation, which means we don't start with evaluating infinity, but we start with evaluating mult. And then for pattern matching, we see that in order to make this first pattern match, there's no need to evaluate infinity because here we have y, and we can instantiate y with infinity, and then we get the result 0. If you, in contrast, compute 0 times infinity, now times is a predefined operator which works in a strict way. So this requires that all arguments are completely evaluated. So this is not leftmost, outermost. This is an exception to the rule. So this will first try to evaluate both arguments, which means it will try to evaluate infinity, and then it runs into non-termination. So this will be non-terminating. Okay, so this is just to briefly recapitulate how expressions are evaluated in Haskell. Now, the big advantage of lazy evaluation is that apart from efficiency improvements, because only those things are evaluated that you really need. Now imagine that it's not infinity, but something which takes 1 hour to evaluate. And then if you want to compute multiplication of 0 and this very time-consuming expression, you would get 0 in 1 step if you do lazy evaluation, and you would take a long time if you would do innermost reduction. So you have efficiency, gains in efficiency, but moreover you can write programs that would be impossible if you wouldn't have outermost evaluation. Namely, you can compute with infinite data objects. So one of the big advantages of lazy evaluation is so outermost evaluation means one can actually compute with infinite objects. And you can already see this here. So this infinity is an infinite object. It's a number which is infinitely big. Nevertheless, you can compute with it. For example, here, we compute with it. We can have expressions which contain this thing, and nevertheless, they give a result. So a first trivial example is we can compute with so computing with a number for infinity. But more interestingly, we can compute with data objects with composed data objects which contain infinitely many sub-objects. For example, we can compute with infinite lists. So the other example is let's compute with infinite lists. Now, to demonstrate this, let's, for example, write an algorithm which gives us an infinite list, and it should be the infinite list of numbers starting from some given number. So we write an algorithm from, which takes a number as an input. So it takes an x as an input, and then it gives us the list x, x plus 1, x plus 2, x plus 3, and so on. And this x can be an integer, can be a floating point, can be any kind of number, so it might operate on any data type A which is member of the type class num. So this type class contains those types where you have something like plus. So you have the integers in there, but also the floating points. So from takes a number and gives you back an infinite list of numbers. And it simply works like this. If you give x to from, then it gives you the list which starts with x, and then from is called recursively with the argument x plus 1. So if you call from of 0, it will give you the list 0, 1, 2, 3, 4, 5, and so on. So this is the list x, x plus 1, x plus 2. And Haskell also has a shorthand for this. In Haskell, you can also write x dot dot. Now we have seen the shorthand where we have A dot dot B. This means the finite list starting with A and going until B. Now if you drop the right border, this will be an infinite list which starts with X and then goes on forever. So you have X, X plus 1, X plus 2. This is simply a different notation. This is the same as from X. Whether you write this or whether you write from X is the same in Haskell. And how can you now compute with such infinite lists? Now, computing, when you compute, of course, you want to have a result after finite time. So, infinite data objects can be used for actual computations, provided that your algorithm only needs a finite part of this infinite data object. So, if you do some computation where you need just a finite part of such an infinite list, you probably don't know how big this part is, but you know that it's just finite, then this can make sense. So computing with infinite lists is possible. This is possible if one only needs a finite part of the list for the computation. So, for example, suppose we have another algorithm, take, which takes a list and a number, and it gives you back the first. It takes a list and a number n, and it gives you back the first n elements of the list. This function is predefined in Haskell, but of course you can also define it yourself. So what take would do is it would take a number and a list and give you back the first elements of this list. So if you want to have the first 0 elements of a list, so the list with the first 0 elements would be empty. If you want to have the first elements of the empty list, no matter how many elements you want, it will always be the empty list. And if you want to have the first n plus 1 elements of a list of the form x and then x's, now how would this list look like? Which gives you the first n plus 1 elements of this list. Right. So the first element of the result list would be x, followed by the first n elements of x's. So in other words, what take does is, if you call take, and then n, and then here you have a list x1 dot 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 xn, xn plus 1, and so on. And no matter whether this list is finite or infinite, it will give you back a finite list, namely the list which consists of the first n elements. So in other words, if we now evaluate the following expression, say take 2 from 5, then of course from 5 is an infinite list. This is the list 5, 6, 7, 8, 9, 10, and so on. But if we just want to have the first 2 elements of this list, the result is a finite list. And in order to compute it, we don't have to evaluate from completely. We only evaluate it a little bit until we know the first 2 elements. And then there is no need to continue the evaluation. So this will terminate. How does the evaluation work? Well, as before, we want to do leftmost, outermost evaluation. To do leftmost, outermost evaluation, we check the patterns. Now, this pattern doesn't match because we have 2 and not 0. And so at this point, we immediately stop and look at the next pattern. Now, this matches everything. Here we have the empty list. Now, we don't know whether this is the empty list or not. So to find out whether the second pattern matches, we need to evaluate from. So we start evaluating from, but we don't evaluate it completely. We just evaluate it one step. And then we get 5 and from 6, or 5 plus 1. Now, of course, we could evaluate further, but we don't do this, because at this point we notice this is not the empty list. This starts with the constructor colon and not with the constructor empty list. So we end up in the last pattern, and there we see everything matches fine. We know this is a number greater or equal 1, and here we know it's a non-empty list, so we can execute the take equation, and we get 5 colon take 1 and from 6. And now this works like this again. We want to evaluate take. In order to evaluate take, we need to find out whether from is the empty list or not. So we get this here. And now we have 5, 6, and take is called recursively take 0 from 7. And now to evaluate this take, we can immediately apply the first equation. There is no need to evaluate from further. We immediately notice that this is the empty list. And that's it. Or if you want to write it in different notation, it's this. So although the list from is infinite, we can compute with it, because due to this outermost evaluation, there are many computations where you don't evaluate it completely. You might evaluate it a little bit. Here it is evaluated a little bit, but not infinitely many times, because we only want to have a part of the whole result. So this shows that indeed one can compute with lazy evaluation. And after seeing this small toy example, let's now try to compute something sensible. So now we want to compute something which is really interesting, benefiting from dealing with infinite lists and benefiting from lazy evaluation. Namely, we want to compute the list of all prime numbers. And there are infinitely many, so we will compute the infinite list of all prime numbers. Okay, so as a larger and more motivating example, we will compute the list of all prime numbers. Of course, we need to have an idea how to do this, and one of the most famous and very, very old algorithms for this problem is the sieve of Eratosthenes. So this was invented by Eratosthenes, who is an ancient Greek. So this was invented 2,000 or 3,000 years ago. So it's an old algorithm, but you can implement this in a very elegant and short way using a functional programming language, and that's probably something that Eratosthenes didn't know. So computing the list of all prime numbers. So the algorithm is not at all new, but the implementation is particularly elegant in this language. And we use the sieve of Eratosthenes. So maybe you know this algorithm from high school. If not, it's rather simple. Okay, so what is the algorithm? The algorithm in natural language looks like this. We start by computing the list of all natural numbers starting with 2. Okay, we know that 2 is the smallest prime number. This information we already have. So generate the list of all natural numbers starting with 2. Now, we know for sure that this list also contains all prime numbers, but a bit too much. So then, afterwards, we delete some numbers from this list. And then the only numbers which remain will be the prime numbers. Now, to delete those numbers, we first mark numbers. And in the next step of this algorithm, we mark the first number that was not yet marked. So in the first step, we would mark 2 because no number is marked. So mark the first unmarked number in the list. So I can execute this in parallel here. So let's say in step 1 we generate this list. 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Now we mark the first unmarked number in this list. Now these numbers are all unmarked, so the first unmarked number is this. I do marking by underlining. Okay, now we executed step 2. Step 3 says delete all multiples of the last unmarked number. In other words, the last, so the highest, delete all multiples of the last marked number. The highest marked number is 2. So delete all multiples of 2. So delete 4, 6, 8, 10. These are all the multiples of 2. Delete all multiples of the last marked number. Okay, so in our example, all the multiples of 2 are deleted. So we delete 4, 6, 8, 10. These are no prime numbers because 2 is the divisor of all these numbers. And we want to delete all those numbers from the list that are not prime, so it's a good idea to delete all multiples of 2. And the last step is go back to step 2. Okay, so let's try to execute this algorithm further. So step 2 says mark the first unmarked number in the list. Now the first, from left, unmarked number in the list is 3. 2 is already marked, 3 is not marked. So 3 we mark now. Step 3 says delete all multiples of 3. Okay, what are the multiples of 3? 6 is a multiple of 3, this is already deleted. 9 is also a multiple of 3, so we delete it. The next multiple of 3 would be 12, which is already deleted because it is even, so it was a multiple of 2. But 15 we would delete now because 15 is a multiple of 3, and so on. And then we go back to step 2. Now we look at the next number, which is not yet marked, and that is 5. And now we delete all multiples of 5 that have not yet been deleted. Now 10 was deleted, 15 was deleted, 20 was deleted, 25 was not deleted yet. 25 is neither divided by 2 nor by 3, but it's divided by 5, so now it's a good idea to delete 25, and so on. And you can see, if we do this infinitely many times, then the only numbers that remain are the prime numbers. We have 2, 3, 5, 7. The next number that we would have is 11, and so on. So this is the standard ancient algorithm to compute prime numbers. And, well, you can also see if we are interested in the first 10 prime numbers, then we don't have to execute this algorithm infinitely many times, but after a finite number of steps, we know the first 10 prime numbers. I mean, already now we know the first 3 prime numbers by this algorithm. Okay, so I hope this algorithm is clear. Now we translate it to Haskell. And, well, how do we translate this by Haskell? We do this basically step by step. Now, the list of all natural numbers starting with 2. Now, that we can get very easily in Haskell. We simply write from 2 if we want to. Or if we want to make it even shorter, we can also write 2 dot dot. This is the same as from 2. Okay, this gives us the infinite list of prime numbers. Now, to get step 2 and 3, what we have to do is we basically have to drop all multiples of a certain number from a list. So to do this, we define the following algorithm, drop mult. And what drop mult should do is it should take an integer and a list of integers and then give us back this list, but in this list all multiples of this number should be dropped. So what drop mult should do is it takes an integer x and a list x's, and it should give us back the list x's. So this is the list x's without the multiples of x. Vielfachen in German, the multiples of x. Now, how can we define this in a very short way, preferably in just one line? Now, luckily we have list comprehensions, so this helps us to do this in a very simple way. So basically we want all elements of xs, but not those where x divides the element. So any idea how to write this in a nice and short way?
List of n's.
Okay.
Where?
Of n's, where?
Okay, n from x's.
N is from x's.
And n mod x is non-zero.
Correct. And n mod x is not 0. So mod is predefined. It's a prefix function. If you want to write it as infix, you have to enclose it in these back quotes. Now this is exactly what you said. If n would be divided by x, then n mod x would be 0. And if n mod x is not 0, well, then n is not a multiple of x. Okay, so this we can write like that. Now what we really want to do is we want to do what we describe here in step 2 and 3. So we want to take a whole list, and then we want to keep the first element, but drop all further multiples of the first element. And then we want to do the same thing with the remaining list. So to do step 1 and 2, I define another function, drop all, which uses this drop mult. So drop all really takes a whole list. So a list which starts with x. And then the idea would be, initially this is the list 2, 3, 4, 5, 6, and so on. And then we would keep the first element, 2, and drop all multiples of 2 from x's. And then, with the remaining list, we would do the same thing. We would keep the first element and drop all multiples of this first element, and so on. So, we would keep the first element, but drop all multiples of the first element from the remaining list. Now, if we do this, then we get the list, and this was the list 2, 3, 4, 5, 6, and so on. Then that would be 2, and here we would have the list of all numbers following 2 without the multiples of 2. And now we do the whole thing again. So we call drop all again. And then from this list, this would start with 3. So now 3 would be kept, but all multiples of 3 would be dropped. And then in the remaining list, we get again a recursive call to drop all. So 5 would be kept, but all multiples of 5 would be dropped, and so on. Okay, and if we have all this, we can now define the algorithm primes, which gives us the infinite list of prime numbers. So primes is simply a list of integers. And primes is just this function drop all called on the list which starts with 2. So this here is the implementation of the sieve of Eratosthenes in Haskell. Now, again, this is not very long. I mean, there are 6 lines and 3 of them are type declarations. Now, if you call primes, if you simply type in this program and then you call primes in in your interpreter, then obviously what will happen is you will get an infinite list of the form 2, 3, 5, 7, and so on. And of course it will not terminate because this list is infinite. Now, if you want to compute the first 100 prime numbers, I mean, this will not terminate, so this is not as elegant as, I mean, you can do it, but it's not elegant. But if you want to compute the list of the first 100 primes, what expression would you have to evaluate in order to get the list of the first 100 primes? Right. You would say take and then 100 and primes. And this would indeed be terminating and give you the first 100 primes. Now, how would you compute, say, the list of all prime numbers which are smaller than 100? This is also a finite list. I mean, there are only finitely many natural numbers which are smaller than 100. So the list of prime numbers which are smaller than 100 is clearly finite. So the list of all primes that are smaller than 100. Now, it might be tempting to write this like this. The list of all x comes from the infinite list primes, but x is less than 100. Now, what do you think? Is this a good idea or not? Mm-hmm. It won't terminate. And why doesn't it terminate?
Because it has a check for each next element is less or
Exactly. So that's the disadvantage. This, if you type in this, it will indeed give you the first 100, all those prime numbers which are less than 100, but then afterwards it will continue searching because, well, you know that the primes algorithm works in a way that numbers get higher and higher, and as soon as you reach 100, there will never be another prime number smaller than 100. But the computer doesn't know that. And indeed, this is what happens. So this is not such a good idea. So a better idea is using something like take. So there's also an algorithm called take while. And this takes objects from an infinite list as long as a certain predicate is fulfilled, and when the predicate is not fulfilled anymore, the algorithm stops. So take while would be something like this. You have a predicate which is a Boolean, can be true or false, and you take the first elements from this list which satisfy this predicate, and as soon as this predicate is violated once, the algorithm stops. So this would be something like take while. So while this predicate is satisfied, okay, in the empty list you get the empty list, but if the list is not empty, so if it's not empty, then you check whether this predicate is satisfied. If it is satisfied, then x will also be in the output list, and take while is called recursively. So this is almost like filter, but in contrast to filter, it stops as soon as this predicate is violated. So filter gives you back all elements from a list which satisfy a certain predicate. Now take while does the same, but as soon as it finds an element which violates the predicate, it stops. Filter would continue, take while does not continue, take while stops. So here, if you now call take while less than 100 primes, this will indeed do what it should do. This is again a partial application. This is a function which waits for an integer and returns true if the integer is less than 100 and returns false if it's greater or equal 100. So this will indeed start computing the list of primes and will give you all the primes which are less than 100. And as soon as you get a prime which is 100 or greater, the algorithm stops. And so this is the better solution. This expression will indeed give you all prime numbers which are less than 100. Now, maybe one last example. And the last example is the so-called Hamming problem, or Hamming list. So this is the last example for using infinite objects. And this is the so-called Hamming problem. So Hamming was a famous mathematician. And this problem is mainly used to test the efficiency of programming languages. So don't ask me what this list actually is good for. It is used as a benchmark for testing programming languages. Now, in particular, what this illustrates is that infinite data objects can be represented as circular lists or circular data objects. Now, what do I mean by circular data objects? For example, think of if you want to produce the list of the infinite list just containing ones, so the list 1, 1, 1, 1, 1. Now this list you can of course define in Haskell like this. A list of integers defined like this. Ones is the list that starts with 1 and then you get ones again. So this is the list 1, 1, 1, 1, 1, 1, 1. Now, whenever a non-function variable, something like this, occurs in its own definition, then you clearly have something which is infinite, and this is represented in the memory as a circular data object. So if a non-function variable occurs in the right-hand side of its definition, then we get a circular data object. This is the internal representation in the memory. So this is, in reality, this is represented like this. You have a certain cell in the memory where you have 1, and then the rest of the list is a pointer which points to itself. So this, it would be represented like this, and ones would be a pointer to this data object. So as you can see, this does not consume a lot of space. It's just a pointer to itself. And the advantage of these circular data objects is that since the representation is extremely small, you don't need much memory, and in particular, algorithms which manipulate these circular data objects also work very efficiently. So this can be used for very efficient algorithms due to this small representation. And okay, maybe I'll give you the algorithm in the next lecture. If you don't know what to do over the weekend, I'll tell you the Hamming problem. The Hamming problem is compute an infinite list of numbers which is ordered. So smaller numbers can be for later numbers. And the only condition is if there's a number in the list, so if there's x in the list, then the list also contains 2 times x, 3 times x, and 5 times x. So that's it. And the question is, this list is clearly infinite, so the list would look like this. You have 1 in there, that's the only condition. Now if 1 is in there, you must have 2 times 1, 3 times 1, 5 times 1. So 2, 3, and 5 must be in the list as well. Now if 2 is in, you need 2 times 2, 3 times 2, 5 times 2. 2 times 2 is 4, 3 times 2 is 6, and 5 times 2 is 10. Now 3 is in the list, so you need 2 times 3, which is 6. You need 3 times 3, which is 9. And you need 5 times 3, which is 15. And so on. And, well, you can continue like this, and the list does not contain all natural numbers. So there are some natural numbers which are not in there, but, well, in particular prime numbers, but except for some very early ones. Okay, the question is how to compute this efficiently. For example, if you want to write an algorithm which gives you the 20th number in this Hamming list, how to do this in a very short time, that's the challenge. And I'll tell you this in the next lecture.